Well, good morning, everyone. Let's get started at this time. We are on section 12.3, and we're going to continue with the topic of dot products. And essentially what dot products allow us to do is to find the angle between two vectors. There are some applications to a dot product that don't involve finding the angle between two vectors, but for the most part it is. And you'll find out later today, I hope, that you can also use it to find the work done. So that's an application that is not directly connected to what we've done, but we are going to be looking at if I can find the damn thing, yes. Some more questions or puzzles, or whatever you want to call them, using the dot product. So here is my first one. This is a puzzle question, similar to question 18. What it says is, we have to find a unit vector that is orthogonal to two vectors. And in this case, it's orthogonal to the vector 1, 1, 0 and to the vector 1, 0, 1. So we're on the hunt for a specific vector. It's a unit vector, so it's 1 unit long, and it's orthogonal to this guy, and it's orthogonal to that guy. And it's using that word we mentioned yesterday, right? Orthogonal just means right angles, okay? In the 3D world, at least. So what we're going to do is we're going to say, okay, if I don't know what something is, would it be reasonable to call it X, Y, Z? Would that be a good start? Right? I don't know who you are, so I'm going to call you X, Y, Z. So if I can find the numbers for X, Y, and Z that have all these properties, right, then I should be able to solve the question. So you're orthogonal to this one. So my vector X, Y, Z dot product with this first vector should be 0. Great. I'm orthogonal. My dot product is 0. And this one ends up being X plus Y equals 0. And I'm going to call that equation 1. I also know that my vector is orthogonal to this one as well. So my vector is X, Y, Z, and it's orthogonal to 1, 0, 1. And so its dot product will be 0. And if you do a dot product, you get X plus Z equals 0. And I'm going to call this guy equation 2. So far, so good. Now, if there are 3 unknowns, and there is here, X, Y, and Z, but right now I only have 2 equations. The logic of math tells me that I need 3 equations, right? 3 equations to solve 3 unknowns. Does that make sense? 2 unknowns, you need 2 equations to do that. 3 unknowns, you have 3. And yet it seems like we've used everything up. But there is one piece of information about my vectors that I haven't used yet, that I should be able to use, and that will help me get my third equation. What's the only piece of information from up here that I haven't used yet?
Its length is 1 unit.
Correct. It's a unit vector. Now, if you want to find the length of this vector, the square root of X squared plus Y squared plus Z squared has to equal to 1. Agreed? And that could be my third equation, but I'm going to employ the just because you can doesn't mean you should rule, and I'm going to use this one instead. Would you agree if you square both sides, this becomes that? Why do you think I'm going to use this instead of that ugly equation? why am I going to use x squared plus y squared plus z squared equals 1 in my calculations rather than use this square root of all that equals 1?
Because it'll be a cleaner calculation.
Yeah, it'll be cleaner, just easier to do. Would you agree square roots are horrible? Mostly. Squares are better. Now, I'm going to take the three equations and we're going to see what we can get out of them. You know, what more we can get out of them. If I subtract y from both sides, or let's me do it the other way. If I subtract x from both sides, then y is equal to negative x, would you agree? And if I subtract x from both sides, z is equal to negative x. And if I rewrite the third equation untouched, then I know all of that equals 1. And that's x squared. Y can be replaced by negative x squared. Z can also be replaced by negative x squared equals 1. Do you see what I've now done is essentially by substitution, have it and I now got an equation with just x's in it. Sneaky. Which means that x squared is a third. And then if I take the square root of both sides, I'm going to take the positive. I know I could take the negative, but I'm going to take the positive, and I'm going to call it 1 over root 3. I could tidy it up, I'm not going to bother. Now, if x is 1 over square root of 3, since y is a negative of x, it's going to be negative 1 over square root of 3. And since z is also the negative of x, it's going to be negative 1 over square root of 3. And there is the vector that we were being asked to find. There we go. Now, if I had made the assumption that it was a negative answer, wouldn't I just get the following? This fella. And that is also correct. But they only wanted 1. So pick whichever one you like. Does anybody notice any connection between the two answers, the only two answers that exist, which is this vector and that one? There is an obvious connection.
They're pointing in opposite directions.
Yeah. One of them's that guy and the other one's that guy. Right. So that's not a surprise then that you got two. So that is just like a one-off question. And it did use dot products, didn't it? In part of the process, at least. And that was question 18. So now we're going to do a new guy. And these do not include dot products, but they're there. So we're going to do them. I'm going to make a very bad attempt. Try my best, but it's going to be pretty bad. Drawing a vector. I'm starting at the origin, right, and moving upwards. And let's pretend that my vector is this vector here. And I'm going to call this vector, and call it any letter of the alphabet I like. I'm going to call it U. And this vector is a unit vector as well. This vector makes 3 different angles. One with the X, one with the Y, and one with the Z axis. And this is where it gets ugly. That's the angle it makes with the Y axis. Maybe if I try different colors, although I don't have that many colors to play with. Well, this one will do. This is the angle that it makes with the X axis. And this angle is the one it makes with the Y axis. Can you see the picture is getting ugly right away? The angle that you make, your vector U makes with the X axis is called alpha. The one it makes with the Y axis is called beta. And the one that makes with the Z axis is called gamma. If you know what these three angles are, you can make a vector cosine alpha, cosine beta, cosine of that gamma. So if you imagine that was 30, this was 60, that was 82, you could create this. This guy here is the vector. And these guys here have a special name. They're called direction cosines. So if you have a vector u and it's a unit vector, and you find the angles it makes with the x, y, and z axis, and you find the cosine of those angles, these are the unit vector. They're called direction cosines. So we can actually find the angle that a vector, a unit vector at least, makes with x, y, or z axis. Let's suppose I have a unit vector, and I need a unit vector. That guy, and that guy. Well, you just trust me, that's a unit vector, right? If I went and said to you, here is the unit vector u, what angle does it make with the x-axis? That would be alpha. Would it not be the inverse cosine of this number? Why does that work? Well, if the cosine of alpha is this, isn't alpha the inverse cosine of that? That makes sense? And if I wanted to know, so that's the angle that my vector makes with the x-axis. If I want to know what angle it makes with the y-axis, we call that angle beta, and it's going to be the inverse cosine of this guy. And then if you want to find what angle it makes, z-axis, gamma, it's the inverse cosine of this guy. And I'm going to find all three of these to show you something that's weird. Do you think these three should add up to 180? Maybe the way I phrased it kind of gave the story away. Let's find out. Make sure that I'm in degrees. I am. Inverse cosine of 3 divided by square root of 14 is about 36.7. Inverse cosine of -1 divided by square root of 14 is about 105.5 degrees. And the inverse cosine of 2 divided by square root of 14 is about 57.7. And if we add those all up, 14, 19, 1, 8, 13, 19, carry 1, 40, 90. There. There's no reason it should be 200 if you're thinking it rounds off to some particular number. If you find the directions or the angles alpha, beta, and gamma using direction cosines, the three angles can add up to theoretically almost anything within a certain range. I mean, you won't get them to add up to 500, right? Well, no, you could. Okay, you won't get them to add up to 1,000 because aren't these guaranteed to be no bigger than how much? What's the biggest alpha can be? Well, we're measuring from the positive, so it's actually 180 degrees, right? So the most you could get is 180, but if one of them was 180, the other two are probably going to be 0, so close to 0. And those are called direction cosines. The only reason I can give you for why this question is bang in the middle of dot products is that if you go and look at the theory of how they calculated this, it was dot products that was used to create it. That's pretty tenuous, but that's why it's there, I would assume. So if I give you, as they do, a vector, and it's a unit vector, you can do this. But what happens if I want to know alpha, beta, and gamma, and the vector that I give you is not a unit vector, but I still want to know what angle this makes with the x, the y, and the z axes? Okay, so what do you think I need to do extra that I didn't need to do here to do that question? I want to know the angle that this vector makes with the x, y, and z axes. In other words, I want to find alpha, beta, and gamma. I can't do it with this number because the inverse cosine of 3 doesn't exist as a real number.
Would you find the magnitude and then multiply by the magnitude?
Well, find the magnitude is a good start, so let's do that. And it's what, 9 add 16 add 1, which I get to be what, square root of 26. What do you think I'm going to do with that number and this vector? And I guess I shouldn't call it V anymore.
Multiply it by 1 over square root of 26?
Correct. In other words, find a unit vector. And since this is a calculation question, there's no point in me making it look pretty, right? No, I'm not going to turn that into, for instance, negative root 14 over 14, because aren't I just going to plug into my calculator? So once you know this, can't you find alpha? I'll just do alpha. I know that the cosine of alpha then is this guy. And so alpha is the inverse cosine of this guy. And if I do inverse cosine of 3 divided by the square root of 26, we get about, it's darn close to, I'll just call it 54 degrees. Okay. That's kind of interesting to me. If you have a unit vector, right? If you have a unit vector, that's this one here, right? Let's call it U. Contained inside its components isn't the information that tells you the angle it makes with the X, Y, and Z axes, right? Contained inside here is essentially the same information, right? That leads to that. So a unit vector isn't just a vector pointing in the same direction as that guy, which it is, but it isn't just that. Isn't it also a vector that tells you the angles it makes with the X, Y, and Z axes, if you just do a little bit more, i.e. this calculation? And one last one of these, and I'm just going to start this one off. We would like to know.
Last page again.
Sure.
Thank you.
We would like to find the angle that that guy makes with the X, Y, and Z axis. So we've been asked to find those guys. And you might say, can't be done. I need numbers, right? I can't do the inverse cosine of C. The calculator's not going to know what I mean. What will we turn this vector into so that we can actually get the direction cosine stuff?
And would we make it into a unit vector again?
We would. So let's see what that looks like. Well, c squared plus c squared plus c squared gets me the square root of 3c squared. Are you happy with that being the square root of 3, big long pause, C? And I'm making that separate, so it's not the square root of 3C, it's the square root of 3 C's, right? How you say it, because it sounds the same both ways. Now, if you want to do this fella and make him a unit vector, don't you do 1 over this guy? C's all cancel out, and guess what? And from this, can't you find alpha, beta, and gamma? And that's how we would solve that question. Are we good? That's the end of those. Now we're going to look at something else. Scalar and vector projections. Of a vector B onto a vector A. Okay, here goes. Suppose I have this vector B, and we'll have them share a common point, and since you can move vectors around any way you like, here is my other vector A. So can you imagine that's A and this is B, right? The scalar, or let's do the vector projection of B onto A. This vector B is going to be dropped on to that vector there, right? And it's going to be done in a very specific way. To be called a projection, you imagine the tip, and can you imagine an invisible dotted line that makes a right angle with vector A? Can you imagine that happening? See that little guy there? Now, if you create a vector, and I definitely don't have enough colors to go around, so it's going to be this color. This little baby vector here, you see it, this guy here? This one I'm doing black. That is called the vector projection of B onto A. Do you see that it's a little baby vector parallel to A, but not quite as long as A, at least in this particular orientation, right? And I'm trying to draw something that's really 3D-ish, right? So you can imagine this is happening in 3D, right? So you got your vectors like this, right? If I did a dot from, oops, here to here, can you see it would be a sloping line as well? And we would like to know what that vector looks like, right? Its components. And if you are finding what's called the scalar projection, I'm going to have to call this something. Let's call it V, because I have no imagination. Right, the scalar projection is the length of that vector. Right, so if that's 2 units long, the scalar projection is 2. And the vector projection, that is the vector itself. And that's what we're going to calculate. And they have a very weird, I like V, but they have a very weird way of writing it down. So here goes. The scalar projection of B onto A, it's called, let's get it here. It's called that. Don't ask me why it's called that, because I don't know. I just haven't bothered to find out. It is a weird naming system, would you agree? But that's what it is. All you need to know is how to calculate it, not what to call it, right? And it's the dot product of A and B divided by the magnitude of A. So at least it's easy to calculate. Right. And that is the scalar projection of B onto A. And the other one is called the vector projection. And that guy is also got an ugly name, which is the projection of B onto A. At least that one's semi-sensible. Can you see the word projection and the A and the B? Right. So that's the projection of B onto A. And this is the scalar projection of B onto A. And it has a formula as well. And its formula is E dot B divided by the magnitude of A squared. So that's a number, A. Now we've got the hard bit over, let me show you the easy bit. Suppose I give you two vectors, A and B, and I ask you for the scalar and the vector projections. Aren't you just going to use these two guys and it's a plug and chug? So I'm going to tell you, making this up, because you don't get a lot of examples. A is the vector 1, 2, -3, and I want to project it onto, projection of B onto A. So I want to do B onto this guy, and B is going to be -1, 1, 0. Pick any two vectors you like, as long as they're not parallel, you're fine. So I want to do the scalar projection. Can I just call it SP, because that's really weird to write. Scalar projection. It's going to be the dot product divided by the magnitude of A. The way this thing is calculated, would you agree this is going to be a number when we're finished? Isn't A dot B a number? And isn't the magnitude of A a number? So two numbers divided, it's a number. If you do the dot product, it's 1 times -1 plus 2 times 1 plus -3 times 0. That's the top. And the bottom is the magnitude of A, which is what? The square root of 1 plus 4 plus 9. And that's 1 and that's 13. So I get that as my answer. Are we cool with that number? Did I do it right? Right. -1, add 2, add nothing, leaves you with 1 on the top.
14 on the bottom.
14 on the bottom. Are we good now? Right. And let's do the other guy, the vector projection, and I'm just going to call it VP because I'm lazy. And it's the dot product divided by this guy squared, A. Well, I already know the dot product is 1. I know that guy's the square root of 14, so when you square it, you get 14. And I know who A is. It's a vector 1, 2, -3. And so I get the answer 1/14, 2/14, and -3/14. Would you agree it's a lot easier to do than it is to explain? Right. Now, I don't know for sure, but I do remember a year or two ago, a student said to me that when you do animations, very often what you do is that you take the shape and it's broken into little triangles or in hexagons or whatever the shape is. And vector projections, and especially, can be used to do the shape and like project it onto the floor and show you the shadow. So if the thing's walking around, you can actually use this formula to show what the shadow would be doing. So the floor would be like the B and the other guy would be the A. I can't verify that, but that particular person was into animation and they said, yeah, that would be how I would do it. Does that make sense to anybody that's in that kind of genre? Can you imagine you wanted, right? Kira, does that make sense that you might want to take a vector and project it onto something else, like a shadow on a wall or something? I don't know.
It helps with light sources and stuff because light sources are always a vector coming down from a particular direction. So if you're trying to change the light source, you got to use the vectors to calculate the shadows.
So this is all kind of done inside the programming without you knowing about it.
Mm-hmm.
Yeah, because if you had to do it with 1 million pixels, you'd be dead, right? Before you finish the animation. Do you know I'm showing my age here. Do you know I am that old that I remember how they used to do cartoons? They drew a picture, and then they did another picture, slightly different, and then they did another one, slightly different. Took a picture of each, and then that gave the impression of movement. Does anybody even know what I'm talking about? But that's how they actually did them. And I bet you today nobody does it that way, with a few exceptions. There's some people who do modeling, you know, the ones that are modeling clay and they move them, you know, move the thing a little bit. Took forever in a day. Useless piece of information, but I've told you it, so we are good. And the questions I'm talking about that dealing with what we've just done here are questions 22, 23, 24. Right, so there's 3 examples of vector and scalar projections. And now our second last guy. There's only one example of this, so I'm going to pick my own version. Suppose you have a force, and that vector is 1, 5, -2. And you are moving that force from position P, 1, 3, 5, to position Q, 2, 7, 11. So in 3D, can you imagine that you've got a guy here, this is P and this is Q, and that you've got a force pulling on it. So you imagine you've got a box and you're pulling it up a hill, but it's like a 3D hill, right? So that hill that I'm talking about is this pen. And the force, well, the most efficient way would be to pull parallel to hill, but you don't always pull parallel to anything, right? So the force is this red pen. So I'm pulling it up the hill that way. The work done is a dot product. It's a dot product of the force vector with the distance vector. And what do I mean by the distance vector? I mean the position PQ. So there's an interesting use of dot products. It, you know, if you're into finding how much work is done, pulling things up slopes, that's the vector showing you the direction that you are pulling it. And this vector is the start to the finish, essentially in a straight line, of course. And so this guy is 1, 5, -2. Now, if you want to get the vector from P to Q, I'm worried she's doing something. What are you doing, Chloe? No, Chloe, no, come here. Chloe, come. You come here. Little bugger, come here. Going to show you. See this? This is a remote. This is not a chew toy. Oh God, she's going to kiss me. She was chewing the remote. Now look at that innocent face. Do you see, like, what did I do? Oh God, you're going to kiss me. No, doesn't count. Bad girl. Aye, aye, aye. Can you see the chew marks? We might not be getting satellite today if that's really bad. Okay. Chloe. Oh, I'm easily distracted. Sorry, everyone. Right, PQ. If you want to find the vector from P to Q, can you do what I do? I call it second takeaway first. So second takeaway first. Second takeaway the first. Second takeaway the first. Are you happy about how you get that very quickly? X component, Q takeaway P, right? Second takeaway first. Second takeaway first. Now, in this particular one, it's 1 times 1 Oh no, she's tuning another one. Yes, yes.
I was very glad when my dog stopped chewing Blu-ray cases. That was a very expensive phase.
Yeah, my uncle's puppy mauled his phone yesterday.
Yeah, she was chewing the other one. In fact, I think she was chewing the other one much longer than she was choosing. Don't you come over looking, no, you're on my, not you're in my bad books. That's it. Okay, 5 times 4, negative 2 times 6, 1 add 20, take away 12. I believe that's 9, so the work done was 9. Hopefully you'd done that while I was gone. Right, there, as far as I know, there's no more buttons for her to chew on, but we shall see. She may have got a stash somewhere of, oh, do you know what, another thing that she loves? She loves slippers. Right? I had a decent pair of slippers, and now I don't. You know, it's one of those fur-lined ones, nice and comfy. Not anymore. Fur is gone. That little bugger, what's she off to? Who cares? Right. One last thing to do, and then I can say we're finished with this, and we'll move on to our next topic. Let's show you what it looks like. I'm trying to, not being very successful today, to make this thing bigger. Or maybe if I make this bigger, that'll do it. Okay. Just try to make it easier for everyone, including me, to see. Nah, wait a minute. Yay, I can make it bigger. Right. The first question that we haven't even covered, and it's the last question, is which of the following expressions are meaningful? And then which ones are meaningless? Meaningful means you can actually calculate the answer, right? And meaningless means it's impossible, right? The answer just can't be done, or it has no meaning. Can you find the expression A dot B, right? So the dot product of A and B with the dot product of a third vector C. And I just noticed darn thing's got the answers. I wish I would stop doing that by default. You did not see that answer, right? You did not see that answer. It still doesn't want to go away, right? This guy is not, has no meaning. Now you say, well, why? Well, if I find A dot B, won't the answer be 5? For instance, 5 dot 3,2, right? 5 dot a vector. Makes no sense, right? Can't do a dot product with a vector. You can only do a dot product with a dot product, right? That's what that's going on. Now, how about the way this one's written? Dot product of a vector C. Oh yeah, could you get 5C? Couldn't that have a meaning? So we would say that has a meaning, and because the answer is a vector, right? Won't the answer be a vector? Now, could you do this calculation? Nods I saw. So if the answer is yes, you have a meaning. Why? Because the answer is a scalar and a vector. No, I don't think I would call it that. 2 scalars.
It's asking if it's the product of that.
Oh, it's a product of. So it's a product of essentially 2 scalars then. Scalar just means a number, right? So that's a number. And isn't that a number? Isn't that a product of 2? Right, I'll let you have fun with this. And that is the end of that section. So let's get a head start on tomorrow's for the next 10 minutes or less. So your next section is going to be called cross product. And I'm just trying to find out what number it is. It's 12, 4. The guy that we just finished doing the dot product has a formula that's pretty easy to write down. And we use it a lot, right? You know, A dot B, length of A, length of B, that kind of thing. The cross product has a formula, which I'm not going to write down because nobody uses the formula. You get the cross product by other means. So let's tell you what it is first. The cross product of two vectors let's call them U and V, is a vector that is orthogonal to U and V. So imagine I have a vector U, looks like this guy, and I have another vector V, looks like this guy. There is a vector called the cross product, which would look something like this vector here. And we use, I should tell you what we call it. It's called U cross V instead of U dot V. That's how you write it. And it's this vector here. And it has the property that it's at right angles to both those vectors. So I'm going to try this with 3 pens, never works well. Can you imagine these 2 pens are U and V? This pen here, which I'm trying to hold, is the cross product. Now if I orientate it, can you see it's at right angles to the blue one? And if I orientate it, can you see it's at right angles to the red one? Make it a little bit more obvious, right? So this thing called a cross product is a vector that's orthogonal at right angles to U and V. And we have a way of calculating it. And there is a formula, which I'm not going to write, as I said. So how are we going to find it? Because that's going to be a big part of the puzzle. Here are 2 vectors, find the cross product. We're going to start with some skill building. If you've done matrices before, which I hope you have, this is a 2 by 2 matrix, right? It's basically a table of numbers. Right? There's a thing called the determinant of it. And those 2 little lines are the determinant of it. And you get it by multiplying these 2 numbers here together, called the major axis. Subtract these 2 numbers here, called the minor axis. So we are finding what's called the determinant of a 2 by 2 matrix, right? In this case, 3 times 3 is 9. Take away 1 times 2 is 2. And the answer I got was 7. Have you seen that before? Some of you at least. Right. Okay. I'll just do one more to show you what it's like. Let's suppose it was 3, 0, -1, 5. Major axis, 15. Take away minor axis, 0. The answer is 15. Easy to do, right? Major, take away minor. Major, take away minor. So how does that help us to get the cross product? Well, here goes. Suppose I want the cross product of the vector 1, -3, 5 with the vector v 2, 4, -2, right? Just randomly picking some digits. You will set up a 3 by 3 matrix The top row is going to be called I, J, and K. You remember those guys I don't like, the I, J, K guys? This is the only time I actually like them, right? They are helpful. The second row should be this guy, because we are going to find U cross V, right? The cross product. So you write down 1, -3, 5. On the last row, you put 2, 4, -2. Are you comfortable how to set up this 3 by 3 matrix? The top row is always ijk. The second row is the first vector, and the bottom row is the second vector, right? And your answer is made up of so many i's, take away, yeah, that's take away, so many j's, plus so many k's. So it's always going to be so many i's, take away so many j's, plus so many k's. So let's show you now. Hopefully that's going to work. Perfect. The number that goes here, right? The so many i's. You cover up the column that's got the i's in. You see that? And we'll keep that guy covered as well. Do you see a little 2 by 2 matrix now? You find the determinant of that 2 by 2 matrix. So let's see how that works. Major diagonal is what, 6? 6 take away 20 is -14. So far, so good? Right. Now, I want the number that goes here, the j component, right? So we cover this guy up, right? Can you see a 2 by 2 matrix? Major diagonal, -2, take away the minor, 10. -2 take away 10 is -12. Last one. The K one, right? If you want the K one, cover up the K column. Major diagonal 4, take away minor diagonal. 4 take away -6, 4 add 6 gets you 10. And then to finish, -14. The negative of that gets you now +12 and 10. Here is your vector U cross V. Do you see that wasn't a formula? Isn't this a process, quite a visual process? Now, I don't have time, but you do. If you take the cross product and you do a dot vector with U, and you take this cross product and you do a dot vector with B, I guarantee, unless I've counted wrongly, that the answer in both cases are going to be 0. Because isn't that I'm orthogonal to the first one U, I'm orthogonal to the second one V. Are we good with that? You can check that yourself, but it will be true. In fact, if you want to check during an exam, isn't that something you could do on your own? Get last name and bye-bye, and I'll hang about for any questions. And I'm going to check where that little girl has gone. Where is she? Oh, I've scared her. She's away, as if I was going to hit her. Shh.
I have a quick question.
Yes.
For the direction cosines, does that actual term refer to the alpha, beta, gamma like variables, or does it refer to like the formula U equals cosine of alpha?
Yeah, the direction cosines are the cosine alpha, cosine beta, cosine gamma.
Okay, so the
It's those
cosine
things.
of each of them.
Right, and the angles it make with the X, Y, and Z axis are the alpha, the beta, and the gamma.
Okay, I just want to make sure when I wrote down the note, I put the term with the right thing.
Yeah, you'll know in the homework what they ask for. I mean, they'll say find alpha, beta, and gamma, right?
Yeah.
So you know you're looking for the angles. But I mean, the language is a little bit vague, because if I say direction cosines, I'm kind of saying both things. I'm saying I've got my vector and it's a unit vector, and I know the numbers will tell me, well, the numbers in a unit vector tell me two things, don't they? Tell me the direction cosines, which are cosine alpha, cosine beta, cosine gamma. because that's just the X, Y, and Z components. And indirectly, it tells me the angles, alpha, beta, and gamma.
Yeah, that makes sense.
Okay,
Okay, thank you.
you're welcome.